Welcome back. So we hear it all the time, right? These huge AI models, the frontier ones, supposedly hitting expert level performance in really specialized fields, like medicine.
Yeah, especially in medical imaging. There's this constant buzz about AI reading X-rays or CT scans as well as, or even better than, trained radiologists.
But here's the thing. Most of those claims, they come from tests using public data sets that are often, well, kind of easy, full of common problems, the stuff that's relatively clear-cut.
Exactly, and that's not the reality of day-to-day high-level radiology. The real challenge lies in the complex cases, subtle findings, the rare diseases, this stuff that really separates an experienced expert from a novice, the tricky diagnoses.
Which makes you wonder, how do these generalist AIs actually perform when you throw those really hard cases at them, the ones that patients and even trainees are starting to tentatively query these systems about?
Well, that's precisely what we're diving into today. There's a really rigorous new academic study that created a benchmark specifically for this. It's called Radiology's Last Exam, or RadLE V1. It's a pilot, but its goal is to test these big AI systems, VLMs, LLMs, on deliberately complex diagnostic cases.
And it's not just about whether they fail, but why.
Exactly. The study provides a systematic framework, a taxonomy really, for understanding the types of errors these AI systems make when faced with visual reasoning challenges. It's quite an academic deep dive into performance and failure modes.
Okay, so we're looking at the methodology, the actual performance numbers comparing AI to humans, and this new way of classifying AI errors. Sounds fascinating. But first, why did they feel the need to create such a tough test? What was the motivation?
Well, the core motivation really boils down to safety and what's actually happening out there. The researchers pointed out this growing trend. You've got radiology trainees using consumer AI tools to discuss difficult cases.
And patients too, right? Uploading their own scans, looking for answers, sometimes even before they see a doctor.
Precisely. And the existing benchmarks, things like Chexpert, they're good for common stuff, pneumonia, obvious fractures, but they just don't test the judgment needed for these really subtle, high-stakes diagnoses. There was a gap.
So RadLE V1 was intentionally designed to be hard, to focus only on the complex stuff, kind of like setting the AI up to fail, or at least struggle.
You could say that. It introduces a specific kind of bias, complexity bias. The curation process was incredibly careful. They gathered 50 really challenging spot diagnosis cases.
And these weren't just random difficult cases.
No, not at all. They came from multiple institutions, and crucially, they were picked by board-certified radiologists, people with at least 5 years of experience after residency. These were cases that had recently stumped clinicians or required that kind of expert pattern recognition.
And critically, these tough cases still had a single, clear, correct answer, right? Based only on the images.
Yes, that's key. A single, unambiguous diagnosis derivable just from the images. No need for patient history or lab tests to muddy the waters. It isolates the visual reasoning aspect just at a very high difficulty level.
What kind of images are we talking about? Was it all X-rays?
Oh no, it was comprehensive. CT scans were the biggest chunk, about 48%. Then radiography X-rays is 26%, and MRI also at 26%. And it covered 6 major clinical areas, including tough ones like pediatrics and head neck neuro, which each made up nearly 20% of the set.
Okay, so a really diverse and challenging set of images. How did they actually test the AI models? Which ones did they use?
They went for the big players at the time, 5 frontier generalist models. OpenAI O3, GPT-5, Gemini 2.5 Pro, Grok-4, and Claude Opus 4.1.
And importantly, they tested them how a regular user might, right, through the public web interfaces.
Exactly. Using their built-in reasoning or thinking modes, just like you or I might interact with them. But for academic rigor, they ran each model 3 separate times on every case, using the exact same standardized prompts.
To make sure the results weren't just a fluke.
Right. To check for reproducibility. And the scoring wasn't just pass-fail either. It was an ordinal scale. 1.0 for a perfect match, 0.5 if the correct diagnosis was mentioned as a part of a differential list, and 0.0 for completely wrong.
Okay, so a nuanced scoring system, but I imagine the focus is really on that 1.0 score, getting the diagnosis spot on.
Absolutely. That's the benchmark for true diagnostic accuracy here.
So let's get to the results. How did the AI actually do on this ultra-hard exam? Was it even close to human performance?
Not even remotely close. The data shows a really massive, statistically significant gap. It's quite stark, actually.
Okay, lay the numbers on us. Where did the human experts land? The ones who picked the cases?
The board-certified radiologists, they achieved 83% accuracy, which is impressive given how tough these cases were designed to be.
83%. Okay, that's the gold standard. What about the trainees, the humans still learning?
Radiology trainees scored 45%, significantly lower than the experts, as you'd expect, but still correctly diagnosing almost half of these very difficult cases. That 45% kind of represents where a dedicated human learner is at on complex stuff.
45% for trainees. So how did the best AI compare to that?
That's the kicker. All the AI models performed worse than the trainees. The top-performing AI, which was GPT-5, only managed 30% accuracy.
Wow, 30%. That's not great.
No. And Gemini 2.5 Pro was right behind it at 29%. So the best AI is substantially underperforming someone who is still in training when it comes to diagnostic complexity.
And you mentioned there were 5 models. Were the others even worse?
Oh, yes. Claude Opus 4.1, for instance, scored only 1%.
1%. That's basically zero, a near total failure on these hard cases.
Pretty much. It really highlights the limits of just taking a generalist model and expecting it to handle this kind of specialized complex task. The overall performance difference across all groups, experts, trainees, AIs, was highly significant statistically. We're talking p-values less than 1 × 10⁻64. Huge difference.
Did it matter what kind of image it was? Like, was AI better at X-rays than CTs?
Well, the humans were better across the board. Radiologists hit nearly 98% on the complex MRI cases, which is incredible.
Wow.
For the AI, interestingly, performance was actually highest on MRI GPT-5, got 45% there, which is closer to the trainee level. But it was lowest on CT scans, where GPT-5 dropped down to just 22% accuracy.
Huh. That's interesting. You might think CT being so detailed would be easier, but maybe the complexity is just higher, more places for subtle things to hide.
It seems that way. The anatomical density, subtle changes.
Yeah.
It appears CT is particularly challenging for these current generalist vision models.
Okay, so the accuracy is low, but was it consistently low? Were the models at least reliable in their wrongness?
That's a great question. And they looked at that using reliability metrics like the intra-class correlation coefficient, or ICC. GPT-5 and OpenAI o3 showed substantial agreement across their 3 runs.
Meaning
Meaning their answers, while often incorrect, were pretty consistent. If you ran the same case again, you'd likely get a similar, albeit wrong, answer. They behaved predictably.
But not all of them. You mentioned Claude Opus 4.1 scored 1%.
Right. And its reliability was rated as poor, and ICC close to 0.
So totally unpredictable. It might give completely different answers each time you ask it about the same image.
Exactly, which is a massive problem for any kind of clinical application.
Yeah.
You need reliability even if the accuracy isn't perfect yet. An erratic system is unusable.
Okay, so the performance is generally poor and sometimes unreliable. Now, there's this idea in AI development, right, that if a model isn't doing well, you just need to let it think longer, give it more computational time for reasoning. Did the study look into that?
It did. And this is a really critical part of the research, I think. They specifically tested GPT-5 using its API, setting it to different levels of reasoning intensity, low, medium, and high effort modes.
Kind of like telling it, okay, take your time on this one, really try hard.
Sort of, yes. It allocates more computational resources and time for the model's internal deliberation process. But the results really challenge that whole more thinking equals better answers idea, at least for this kind of task.
What did they find? Did accuracy jump up in high effort mode?
Hardly at all. In low effort mode, GPT-5 got 25% accuracy on these cases. In high effort mode, it got 26%.
Wait, that's it? Just a 1 percentage point gain?
1 single percentage point. Statistically and clinically insignificant, basically noise.
Okay, but what about the cost? How much longer did it take to get that tiny, tiny improvement?
That's where it gets really stark. The low effort mode took, on average, about 10.5 seconds per case, which is, already a bit of a wait.
Yeah.
The high effort mode average latency was 65.6 seconds, over a minute.
Whoa, so you wait 6 times longer.
Over 6 times longer, yeah.
For essentially no improvement in diagnostic accuracy.
Precisely. That minimal gain comes at a massive cost in terms of computation time and, practical usability. Imagine a clinician waiting over a minute for an answer that's still wrong 74% of the time.
Yeah, that's just not viable. It really suggests that the problem isn't just a lack of thinking time, doesn't it? It's something more fundamental about how the AI is processing the images or linking findings to diagnoses.
Absolutely. It implies a core architectural limitation. Simply throwing more computation at the problem, making the model deliberate longer, doesn't fix the underlying issues in visual perception or diagnostic reasoning for these complex medical images. The cost vastly outweighs any benefit.
So if making the AI try harder doesn't work, we need to understand how it's failing. Did they get into the specific types of mistakes?
Yes, and this is where the study gets really insightful, moving beyond just the numbers. Because the performance gap wasn't fixed by more computation, they developed this systematic way to classify the types of visual reasoning errors the models were making.
A taxonomy of errors, specifically for these vision language models.
Exactly. They drew inspiration from existing frameworks used to analyze human errors in radiology, but adapted it for AI. It's quite an academic contribution in itself.
Okay, so what are the main categories? How do these AIs mess up?
They grouped errors into three main types. The first is probably the most fundamental, perceptual errors. This is about failures in basic visual recognition, just not seeing things correctly.
Like missing something that's actually there.
Right. That's called underdetection. A key example they gave was GPT-5 completely failing to see the visible ballooning, the dilatation of a ureterosol on the images. That's a crucial visual sign, and it just missed it.
Or the opposite, seeing things that aren't there. Hallucinations.
Exactly. Overdetection. In that same ureterosol case, GPT-5 confidently reported seeing multiple cysts in the patient's kidneys, which were actually normal. These hallucinated cysts sent its diagnosis way off track.
Okay, so first category is just failing to perceive the image accurately. What's next?
The second category is interpretive errors. This happens when the model might actually see the finding correctly, but it fails to connect that finding to the right diagnosis. It messes up the interpretation.
Can you give an example?
Sure. One type is misinterpretation or misattribution. They had a case of an acromioclavicular, or AC, joint dislocation in the shoulder. GPT-5 correctly noted that the clavicle was elevated. It saw the sign, but then it concluded the diagnosis was a posterior shoulder dislocation.
So it saw the piece of evidence but linked it to the wrong condition.
Precisely. Linked it to a different and actually more serious shoulder problem. Another interpretive error they saw was premature diagnostic closure, basically, jumping to a conclusion too quickly without considering other possibilities that fit the findings, like settling on one diagnosis when the features could suggest several things.
It sounds very human, actually. Jumping to conclusions.
It does, doesn't it? And the third main category also feels quite relevant to how these models generate text. Communication errors. These are internal inconsistencies within the AI's own reasoning output.
Like contradicting itself.
Exactly. The most common form was finding summary discordance. The model might generate a detailed text description correctly, identifying several abnormalities, say hyperinflated lungs and a skinny heart shadow on a chest x-ray. But then, in its final summary line, it concludes, normal chest radiograph.
Wow. So the detailed observations completely clash with the final answer.
Right. It shows a breakdown in the internal logic connecting the descriptive process to the final judgment. The model can't maintain coherence.
It's fascinating how these error categories almost mirror the ways humans can make diagnostic mistakes. Did they draw parallels to human cognitive biases?
They did. They noted that the patterns of AI failure often resembled known human cognitive biases. One prominent example was availability bias.
Meaning the AI favors diagnoses it remembers more easily from its training data.
Kind of, yeah. Because the massive training data sets are inevitably skewed towards common, often acute, conditions like pneumonia or embolism, the models developed a tendency to default to those diagnoses. Even when faced with subtle findings pointing to a rarer condition, like scimitar syndrome in one case, the AI would often ignore those subtle clues and jump to a more available common diagnosis.
So it's overconfident about the common stuff it saw millions of times during training, and that blinds it to the rare but important findings.
That seems to be a major limitation. It's biased by the sheer volume of common cases in its training diet, making it less sensitive to the nuances of rare, complex presentations. #tag outro. So if we kind of pull all these threads together, the message from this RadLE V1 benchmark study is, well, pretty unambiguous. These frontier generalist AI systems are performing substantially below both expert human radiologists and radiology trainees when faced with complex, diagnostically challenging cases.
Which really pumps the brakes on the hype, doesn't it? It provides strong evidence against just letting these systems loose in clinical settings without supervision, especially for difficult cases. Whether it's clinicians using them or patients trying to self-diagnose, the reliability just isn't there when complexity increases.
Absolutely. And it has major implications for regulation. The researchers argue quite strongly that regulatory bodies shouldn't rely solely on benchmarks testing common conditions. To really assess safety and utility, evaluations must include performance on high-complexity cases, like the ones in RadLE v1.
It really shifts the focus for future development, too. Clearly, just making the models bigger or letting them think longer isn't the answer here.
Right. The path forward seems to require fundamental improvements in detecting subtle visual findings and achieving more consistent diagnostic reasoning. It suggests that maybe specialized models, fine-tuned specifically for medical imaging tasks, might be more promising than trying to make these massive generalist models do everything.
They need better eyes, essentially, not just bigger brains.
You could put it that way. Trying to force-fit this task onto a generalist architecture seems inefficient and, based on this data, largely ineffective for the hard stuff.
Which brings us neatly to our final thought for you, the listener, to chew on. We saw that high-effort reasoning costs 6 times more time for almost zero accuracy gain. And we saw that many core errors were perceptual, the AI failing to see correctly. So the question is, what kind of fundamental architectural change, something beyond just more compute power, do you think is needed to actually allow AI to perceive and interpret the incredibly subtle visual nuances required for expert-level medical diagnosis?
It's not about thinking faster, it seems. It's about seeing smarter and figuring out how to build that smarter vision into AI. Well, that seems to be the real frontier now.
So today, we're diving into what feels like a high-stakes showdown. In one corner, you've got the collective wisdom of human medical expertise, and in the other, some of the most powerful AI ever created. And it all comes down to something called radiology's last exam. And look, this isn't some sci-fi question anymore, right? I mean, we all hear the headlines. AI beats doctors at exams. But when it's your scan, a really complex one, how good are these things, actually? The thing is, these super powerful AI models, they're already out there. You've got doctors, trainees, even patients just uploading their own scans and getting these AI interpretations. The hype is, well, it's huge. So some researchers over at Ashoka University decided to ask a simple but really important question. What happens when you get past the easy stuff, the textbook cases, and give the AI a test that's actually hard? Okay, so here's how we're going to break down this incredible study. First, we'll tackle the problem of AI hype in medicine. Then, we'll look at how they built a much tougher exam. After that, we'll get to the scores, you're going to want to see this, and we'll dig into why the AI had such a hard time. And we'll wrap it all up with the final diagnosis on where things stand today. All right, so first up, let's just set the scene. We're constantly hearing about expert-level AI, but there's this big gap opening up between what's claimed and what's actually happening in a real clinic. And a huge part of the problem comes down to the data. See, most of these AI models get trained on these huge public data sets, and they're packed with really common, obvious diseases. And that's great for learning basic patterns, but that's just not what real-world radiology is like. The real skill of an expert radiologist isn't just spotting a simple fracture. It's about seeing that one tiny, subtle thing that a trainee might miss. That's the real test. And this is where things get really urgent. You know, this isn't just some debate for researchers. The study makes this really crucial point. Actual patients are using these AI tools you can find online. They're getting medical advice, and sometimes they're trusting the AI's answer more than their own doctors. So yeah, we need to know how good these things really are. So to cut through all that hype, these researchers decided they needed to build a totally new kind of test, one that was designed to be hard, an exam that would really push these AIs to their absolute limits. And they called it RadLE, which stands for Radiology's Last Exam. You can think of it like the super hard final exam you'd have to take to become a board-certified radiologist. It's made up of 50 really tough spot diagnosis cases. These are the kinds of tricky images where you get no extra info, no patient history. You just have to look at the image and know what you're seeing. It takes real expertise. And this wasn't just one type of scan. The test was really comprehensive. Almost half of the cases were complex CT scans, and the rest were split evenly between MRIs and good old-fashioned radiographs, or X-rays. That variety is key, right? It means the AI couldn't just get lucky by being good at one single thing. All right, so let's meet the competitors. On the human side, you've got your seasoned, board-certified radiologists, and you've also got radiology trainees. And facing off against them, a who's who of the latest and greatest AI models out there. GPT-5, Gemini, Claude, the whole crew. So the stage was set. Okay, so it's time for the big reveal. The results. How did everyone do on this super tough exam? Well, the scores were, let's just say they were pretty clear and honestly a little shocking. So first up, let's look at the human experts, the board-certified radiologists. They set the bar high. They nailed an incredible 83% of these ridiculously hard cases. That's our gold standard. Okay, what about the trainees? They came in at 45%. And that's a really important number, right? It shows you what someone with a lot of training but not decades of experience can do. And now for the AI. The best AI, the top of the class, scored just 30%. So the takeaway here is pretty stark. The best AI we have right now did way worse than a human trainee, and it wasn't even close to an expert. And when you look at the full results here, the picture becomes crystal clear. I mean, just look at that gap. You've got the expert radiologists way up top, then a big drop to the trainees, and then way down here, you've got all the AI models clustered together. It's a huge reality check for anyone who thinks AI is ready to take over. But the researchers didn't stop there. They wondered, hey, what if we just make the AI think harder? So they tried running GPT-5 with different amounts of reasoning effort, and the result was wild. Cranking the effort from low to high only gave them a tiny 1% boost in accuracy, but it took 6 times longer to process. So basically, more thinking didn't mean better answers. It just meant a lot more waiting around. Okay, so we know the AI pretty much bombed the test, but maybe the most important part of this whole study is digging into why. The researchers didn't just give the AI a grade, they did a deep dive on every single mistake. And to do that, they came up with this really smart new framework. They call it a taxonomy of visual reasoning errors. It's basically a system for classifying all the different ways an AI can mess up when it's trying to read a medical image. This lets us go way beyond just saying it was wrong and helps us understand these specific ways it's failing. This whole system really breaks down into 3 main categories of errors, which give us a really clear way to talk about what's going wrong. First, you have perceptual errors. This is when the AI just doesn't see the image right. It either misses something important or, and this is a big one, it makes something up that isn't there. Second, you've got interpretive errors. Here, the AI might see the right thing, but it completely misunderstands what it means medically. And third, and this one is fascinating, are communication errors. This is where the AI's final answer actually contradicts its own reasoning that it lays out. It's like a total breakdown in its own logic. So let's zoom in on one of those perceptual errors, overdetection. This is what you and I would probably call an AI hallucination. It's when the model is absolutely convinced it sees something in the scan that just doesn't exist, and it reports it with total confidence. And this is where you see how dangerous this can be. For example, in one of the cases, the AI completely missed the real diagnosis. But it didn't stop there. It actually hallucinated, and I'm quoting here, multiple cysts with a spider-like pattern in the patient's kidneys. And based on this thing it just made up, it confidently diagnosed the patient with polycystic kidney disease. That's a really serious condition that this patient absolutely did not have. A total failure of perception. So, okay. We've seen the AI take the toughest test imaginable, we've seen it fail, and we've looked at why it failed. So, what's the final diagnosis from the people who ran the study? Well, their conclusion is really clear, and it carries a lot of weight. They basically say that, look, while these AI models are impressive in a lot of ways, they are absolutely not ready to be used on their own for complex, high-stakes medical diagnoses. They're just not reliable enough to be let loose without a human expert in the loop. And that really leaves all of us with a huge question for the future. Because as these tools get more and more woven into our healthcare, we have to figure this out. When an AI gets it wrong, makes a huge life-changing mistake like the one we just saw, who's on the hook? Is it the company that built the AI? Is it the doctor who decided to use it? The hospital? That is the tough conversation that research like this is forcing us all to have, and we need to have it soon.